Hello guys, welcome back to my channel Digamma again. Apologies for the break. I was on vacation and now this is one last video I would like to make before I go back and start another semester at university. This one's a really nice question. It was in one of the Olympiads, although I can't really cite a source for this. It appeared on one of the Instagram pages. I personally couldn't solve it or was too lazy. I may have gotten the first part right, but whatever. I think this deserves to be posted on my YouTube channel. So let's get started. Whatever we have, let's just call it L. L is 1 over 1 to the fifth plus 1 over 1 to the fifth plus 2 to the fifth plus 1 over 1 to the fifth plus 2 to the fifth plus 3 to the fifth and so on. So how can we generalize this? Well, you see the bottom, the denominator is its own independent infinite sum going on, where this last term or the range of it is determined by the position in it of that entire term in the series, the entire series. So what we can do is we can have I go from say 1 to infinity because it's infinite, 1 over sum j equals 1 to I j to the fifth. So what this is going to do is I is basically the position or what term number it is in the series. So for the first term I is 1, so j goes from 1 to 1, so there's just one term, 1 to the fifth, and we have that. For I equals 2, j goes from 1 to 2, so we have two terms, 1 to the fifth plus 2 to the fifth, because there's an independent sum going on in the denominator itself. So you see there's a nice nested structure, but however it is nice, it's not really that easy to solve because we can't really rearrange even if you wanted to. Usually what we do is we try to rearrange this and see if there's a better form to work with than whatever we have. Well, we can't in this case because it's the sum's in the denominator and it's way more complicated than just having the sum up front. So we can't rearrange. What about some telescoping, converting it into a telescoping series, because that's the cleanest way of doing it? Well, big no for that because clearly you can't do that. But what can we do? Well, we'll have to brute force solve the inner sum first, express it in terms of I because it's finite, and then solve the entire infinite sum. So the first sum is a finite sum of is a power sum of fifth powers. So let me just change my color a little bit. We have a nice formula and I might prove this in the future, but I don't know how necessary this is. K to the fifth is n squared times n plus 1 squared 2n squared plus 2n minus 1 divided by 12. So all we need to do in the question we had before us is just change, instead of having an n, we're going to have i's. So L now becomes sum I equals 1 to infinity. Well, the 12 is in the denominator of the denominator, which will go on top by reciprocity. And all the I terms remain. So I squared, I plus 1 squared, I squared plus 2I minus 1. And we need to work with this form. Well, this is really impossible to solve in this way, in the current form it is in. So what we're going to do is use partial fraction decomposition. So we want to split. Let me just keep changing colors. I have a bad habit of sticking to the same color. We want this to look like at least the non-sum part, this is the summand, to look like some constant over I squared plus b over I plus 1 squared plus c over I squared plus 2I minus 1. Well, you might ask, why didn't we stick to the regime we had in integration where we sort of took linear terms, especially like here, ci plus d? Why didn't we do that? That's because having a lesser power that's one less than the denominator is useful for integration, because then you can just use the chain rule, reverse the chain rule by a u substitution, and you have a natural log, something in terms of a natural log. Here we don't really need that. Having an I on top, any factor of I, is going to cause problems for evaluating this infinite series. So 12 is equal to, I take the common denominator in this case and cancel it out from both sides. So I have all these terms that were sort of, I believe, multiplied together. I made a mistake here. Apologize for that. There was supposed to be that other term. I didn't really write that out explicitly. I plus 1 squared, I squared plus 2I minus 1. And we have I plus 1 squared so I squared so we write the terms that weren't there initially in its denominators. That's how this common denominator magic works. Okay, and now what we're going to do is plug in I equals 1 in the entire equation. So 12 remains the same, it's a constant. The I squared factors will go to 0 because they have this as their factor. So for the A, we're going to have A times negative 1, which means A is negative 12. Fine, nice. Now I equals negative 1. Doing that, all these A and C will go away because they have I plus 1 over there. B, and 12 remains the same. We'll have a negative 1. So this just means that B is negative 12. There you go. Nice. So far so good. Now we can't really do the same magic for finding C because, well, the roots of this are irrational, and working or adding, subtracting irrational numbers is kind of messy. You don't really want to do that. So just plug in any arbitrary number. Let hope for something that's easy, because make your calculations a lot easier. 12 equals A times 4 because of 2 squared, 2 plus 2 minus 1. I'm just doing the algebra quick. I don't want to waste your time. Plus C times 4. We know what A and B are, so plug in that information. So now divide by 12. We have 1. I believe negative 12 from the 4 and 3. Negative 3 plus C by 3, 4 by 12 is 1/3. So C is, this is negative 15 plus 1, 16 times 3 is a 48. Nice. We know A, B, and C, which means, and our systems of equations were consistent, which means this regime of using partial fraction decomposition was indeed successful. So, and now let me just revert back to our original color. We can really split our infinite sum into 3 infinite sums, going from 1 to infinity each. So A is I squared, sorry, since we have negative 12 over I squared plus sum from I equals 1 to infinity minus 12 I plus 1 squared, and then C is positive 48. So we have 2I squared plus 2I minus 1. Well, the nice thing is we know how to solve the first one. That's just the Riemann zeta of 2. That's Basel problem. That's pi squared over 6. Second one is kind of like the first, except we had the sum starting from 1. Here the sum starting from 2. So we need to add and subtract. So when we add that this sum will include the 1, it will become pi squared over 6, but we have to subtract 1 from it, and of course we have a negative 12 factor we need to account for. This crazy infinite sum that we don't really know, I'm going to call that S. So it has a prefactor of 48 from the partial fraction decomposition. This will become a negative 2, this will become a negative 2 and a 12. So we have 12 minus 4 pi squared plus 48S. That's what we want to find. That's L. So now I'm going to solve S on a fresh page because we really need to do lots of work for this. Okay, this is what we have for S. Now we want to this is a quadratic, we would like to split it up by partial fraction decomposition. So let's just find its roots just quickly. So using the quadratic formula, we have this, which reduces down to minus 1 plus or minus square root of 3 over 2. Fair enough. These are your roots. And now if you want to write this polynomial as a product of its roots, you need to have coefficient 1 on the leading term, which is I squared. So we need to pull the 2 out of everything. See, this is standard procedure. Bear with me. Because many viewers, they don't really have this clear with them. And now, by doing that, can we really write our sum as a product? So I minus, and this minus will become a plus 1/2 minus square root of 3 over 2, and then the other root, which was plus 1/2 plus square root of 3 over 2. Fair enough. And now I would like to do a partial fraction decomposition on this thing itself. So just choosing a better color. So we want to have the summand of S as some alpha over I plus 1/2 minus square root 3 over 2 plus beta over I plus 1/2 plus square root 3 over 2. And again, we have the factor of 1. I'm forgetting the 1/2 for now because it's outside. Alpha times 1, I plus 1/2 plus root 3 by 2. Beta times I plus 1/2 minus cube 3 over 2. And now I would like to plug in the first root, like take the value for the first root, set that equal to I. And when I do that, I will have I equals, well, the first guy just disappears. Beta times negative root 3. So beta is negative 1 by root 3. For alpha, it's simple, really. You put the positive root in. So that way, beta disappears. And alpha remains to be the square root of 3. So alpha is 1 over square root of 3. We have our partial fraction decomposition with us. So switching back to color blue. Blue is the color of progress for us in this case. I'm going to pull out the 1 over square root 3. We have a sum I equals 1 to infinity 1 over I plus 1 half minus root 3 over 2 minus sum I equals 1 to infinity 1 over the other guy, so 1 half plus root 3 by 2. And now if you notice some infinite sums like this, where you have some linear term which is offset by some factor, so it's not really harmonic but close harmonic in the sense that it's offset by a small factor. Remember, the digamma is the solution, because if you remember my 2020 epic sum video, we did the similar approach with that, except we had imaginary factors. The formula for digamma of the infinite series representation is negative Euler-Mascheroni constant sum from n equals 0 to infinity 1 over n plus 1 minus 1 over n plus z. I proved this in a video, check that out. And now I would like to sort of have a negative version of this, except instead of z I have a z naught changed parameter. So I have a plus Euler-Mascheroni now because I switched everything around. Sum from n equals 0 to infinity. Negative switched everything around, so I have n plus z naught in this case minus 1 over n plus 1. Notice the common factors are going to die down, which means the Euler-Mascheroni goes away. Anything that only depended on n will go away, which means this and that. So all we have left, so digamma of z minus digamma of z naught, is just sum from n equals 0 to infinity 1 over n plus z naught minus 1 over n plus z. Well, this looks kind of close to what we had there. We can set z naught to be 1 half minus square root 3 over 2 and z to be 1 half plus square root 3 over 2. And then we just have to switch the order when we're writing the difference of digammas, and that's literally it. This was the great insight. And now it's time to go back to do our calculation, except there's a small problem. You see that our sum starts from a 1 here. So how are we gonna battle that? Well, why don't we add the 0 term independently and then subtract that, add and subtract, so it's like adding 0. So when we add that, we can with our heads held high start the sum, make the sum run from 0, but also don't forget to subtract the 0 term, since we've added it by changing the index like this. So we have 1 I plus 1 half minus root 3 by 2, and I'm subtracting the 0 term. The 0 term is 1 half minus square root 3 over 2 in the denominator, so the 2 goes on top. 1 minus root 3, that's the 0 term, I subtracted that, minus sum I equals 0 to infinity 1 over I plus 1 half plus root 3 by 2, and then minus plus the 0 term, which is 2 over 1 plus root 3. And now, well, just work with these terms. You see some stuff is going to cancel off if you take a common denominator here. So 1 minus 3 squared, root 3 squared is a negative 2. That's your first term. And then you have a difference of these guys as we planned to set them. Yeah, my brackets weren't large enough. And now notice this cancels off nicely. Everything just works out to give us 1. So we just have a 1 plus. Now for this, remember the digammas over here were flipped up. So digamma of 1 half plus root 3 by 2 minus the digamma of 1 half minus root 3 by 2. Whenever we have a difference of digammas, we have to look for one thing if we want to achieve a closed form. And in questions like this that appear on some Olympiads, they usually have closed forms. So remember the deflection formula for the digamma function. I again proved this in the same video where I derived the reflection formula for the gamma function. It's pi times cotangent of pi z. It's really, you can derive this from the reflection of the gamma function itself. So if you want to have this form, we need to have z equal to the second parameter, which means we need a negative root 3 by 2. Because if you work this out, 1 minus 1 half is 1 half, minus minus plus, and we indeed get this first term. So which means we can finally use the reflection formula after all. So if pi times cotangent of whatever z was times pi, so that's pi over 2 minus pi over 2 root 3. And that's indeed what we have there. So let's just plug and chug. Everything's working in our way. That's really nice about these kinds of questions. So we just have a pi. Oh, but don't forget this factor. I forgot it there. So pi over 2 root 3 cotangent of pi over 2 minus pi over 2 root 3. Well, we can use the complementarity property of trigonometric functions to convert this into a tangent. Pi over 2. Wait, did I mess something up? I might have. I'm just checking. I don't want to. No, it's all, yeah, it's all fine. Just checking. Don't want haters in the comment section. Okay, this is our final form for S, and now it's time to put this back into L for the conclusion. So L is 12 minus 4 pi squared plus 48 times S, and S, we did our number crunching as true mathematicians would, to give us a tangent of pi over pi times square root 3 over 2. So just simplify it. That's all that remains to be done. We have a 48, 24 pi over root 3, tangent of pi over 2 times square root of 3, and just simplifying, we have 60 minus 4 pi square. Well, this is 8 times 3. That 3 will cancel out with this root 3 to give us 8 pi times root 3, tangent of square root 3 over 2 times pi. And that is indeed your solution for crazy nested quintic infinite series. That's your answer. Hope you're satisfied. This was a really nice solution. I figured out in my mind when I was trying to solve this that we have to use the finite powers sum formula for the quintic powers, but then I was lazy about the partial fraction decomposition because there were lots of terms. Anyways, Hope you enjoyed it. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. In the meantime, stay home, stay safe, keep doing math. Peace out. I'll see you next time when I am in the United States, halfway across the world. See you later.